Hi everyone, I'm Jeevidan Alagraja. I'm going to present our work on scale invariant learning from trapezoidal data streams. Trapezoidal data stream, known as a number of instances and the feature space simultaneously grow over the time. For example, as shown in the figure, the feature space grow over the time. Your classifier should be able to add up this feature space. Traditional machine learning assume features of instances are scaled to have zero mean and a standard deviation of 1. But in contrast, streaming features have arbitrarily different feature scales. So, learning algorithms should be able to add up regardless of the feature scale. We bridge the gap between trapezoidal data stream and the scale invariant learning in this work. We focus on learning to classify instances from trapezoidal data stream where features of the instances are not scaled to have uniform distribution. Let's see what are the drawbacks with the state-of-the-art algorithms to handle this problem. The state-of-the-art algorithms rely on the prior scaling of the features, which is not feasible in the data stream because we assume data streams are infinite. The state-of-the-art algorithms are more sensitive to feature scaling. The arbitrary feature scaling will end up poor performance classifier. Online gradient descent kind of algorithm should be tuned carefully to get a better performance. To get this better performance, you need a knowledge of optimal classifier and the future gradients. In a recent work, I achieved a similar record bound as an online gradient descent with a separate learning rates by using above equations. Here, phi is denoted for scale-free gradient and W is denoted for weights for the prediction, and here G is denoted for cumulative sum of negative gradients and V is denoted for cumulative sum of squared gradients, and M is denoted for maximum value of the features encountered, and F is denoted for convex function. We provide variation of this algorithm for trapezoidal data stream. To achieve this, several challenges need to be addressed. The first challenge is incorporating the growing feature space into the classifier. So we simply extend the classifier for the new feature space while keeping the loss small. There should be a feature selection method since there is no bound for the incoming features. So we introduce sparsity method to prune out the insignificant features at every round. We provide the details of the algorithm. Here, alpha is learning rate of algorithm, which is calculated with average prediction it makes, maximum value of the features encountered, frequency of features, and current value of the features. From that, we calculate weights for the prediction as shown here. Then we apply sparsity method to prune out insignificant features from it. Then weights are scaled according to the equation 1 shown in previous slide. Prediction and parameter update is made respectively. This algorithm shown conservative behavior to the extreme changes in the feature values, as its learning rate dependent on maximum value and the current feature value. We provide second algorithm as it makes more aggressive update. Here, weights are calculated according to the equation shown here. After, we prune the less effective features from feature space. The weights are scaled for the prediction and the prediction and the parameter update is made respectively. Here, learning rate is updated according to how good or bad we performed in a classification task. More simply, the learning rate is updated as reward function. We provide experiment details in this slide. To simulate the trapezoidal data stream, we split each dataset into 10 sets. For the first set, we remove 90% of the features and they only carry 10% of the features. And the second set, it removed 80% of the features and only carry the 20% of the features. Likewise, we continue to do this and leave the last set with 100% of the features. We compare our results with state-of-the-art method online learning from streaming features. You can clearly see we outperform their method 7 out of 9 datasets. It shows when features have arbitrarily different scales, our method outperforms state-of-the-art by big margin. Thank you so much for listening and leave your feedback.